Hey there, and welcome to The Explainer. So when we picture the future, whether we're talking about deep space exploration, next-gen defense tech, or even crazy breakthroughs in medicine, we usually immediately think of advanced AI, right? Or massive software updates. But actually, the real magic driving tomorrow's innovations isn't just sitting in the code. It's out here, in the physical world. It's advanced materials. We're talking about substances with literal superpowers. Think metals that can remember their own shape, sheets of carbon literally a single atom thick, and solids that just look like, well, frozen smoke. Let's get into it.
Okay, here's our game plan for today. First up, we'll look at the magic of smart materials. Then, we'll talk levitation and zero resistance. Third, we're covering frozen smoke and super sheets. After that, healing and power generation. And finally, stick around for part 5 because we're going over some absolutely crucial exam traps and memory tricks for you. Let's dive in.
All right, part 1, the magic of smart materials.
To put it simply, smart materials are substances that respond completely automatically to changes in their environment. Imagine a material that can actually sense when the temperature drops, or when the pressure changes, or reacts to an electric or magnetic field, or even just shifts in the light. And then it adapts on its own. They essentially have built-in sensing abilities. A really cool real-world example of this is self-healing materials used in construction. Think about polymers injected into concrete that can actually repair their own cracks to keep a building standing strong. I mean, it's almost like living tissue.
And speaking of almost living, let's talk about shape memory alloys, or SMAs. These are incredible alloys that literally remember their original shape, and they just snap right back to it the second they're heated. The absolute classic example here is nitinol, which is an alloy made of nickel and titanium. Seriously, think of this as a real-world superpower. It's absolutely crucial in aerospace for building smart, adaptive airplane structures. And in medicine, we use it for cardiovascular stents that expand perfectly once they reach body temperature inside an artery. Or honestly, even the braces straightening your teeth. Now, this shape-shifting magic really boils down to a super simple 3-step formula. First up, deformation. You bend or crush the material totally out of shape. Second, heating. You apply some warmth. And third, boom, it snaps right back to its original form. It's such a simple mechanical process, but it has absolutely revolutionary applications across robotics, aerospace, and biomedical engineering.
Moving right along to Chapter 2, levitation and zero resistance.
Zero. Okay, the absolutely crucial point here is this exact number. When we talk about superconductors cooled to extremely low temperatures, they hit exactly zero electrical resistance, literally zero. That means electric current flows through these materials without losing a single drop of energy. Imagine a nationwide power grid where no electricity is lost to heat along the wires. That is the absolute holy grail of power transmission. But wait, it gets better. Superconductors do something else completely mind-bending, called the Meissner effect. This is perfect diamagnetism. Basically, a superconductor violently pushes away any magnetic field from inside itself. And because it expels that magnetic field so perfectly, it actually makes magnetic levitation possible. Objects literally float in midair. This is the exact physics principle that lets those massive high-speed maglev trains just hover right above the tracks, completely eliminating friction. And as you can probably guess, these zero resistance and levitation traits are totally revolutionizing a bunch of diverse sectors. MRI machines in your local hospital, they rely on superconductors for their massive magnets. We've got maglev trains for frictionless, ultra-fast transport. Particle accelerators rely on high magnetic fields to explore the fundamental physics of our universe. And of course, the dream of perfectly efficient electricity via completely lossless power transmission.
All right, part 3, frozen smoke and supersheets.
Frozen smoke. I love this. This is the highly visual and honestly brilliant nickname given to aerogels. If you hold one, it literally looks like a little hologram of a cloud resting right in your hand. Aerogels have extremely low density and incredibly high porosity, which makes them unimaginably lightweight. But hey, do not let their delicate, airy look fool you. They are actually some of the most phenomenal thermal insulators humanity has ever discovered.
Because they are such great insulators, this airy, frozen smoke handles some incredibly heavy-duty jobs across major sectors. Up in space, aerogels provide vital thermal insulation, shielding spacecraft and rovers from the freezing extremes of the cosmos. Down here on Earth, they're used as advanced insulation materials in building construction. Plus, because they're basically mostly empty space and highly porous, they act like massive sponges. This makes them incredible absorbents for environmental emergencies, like soaking up oil spills in our oceans. So, if aerogels are all about airy volume, graphene is about flat, microscopic perfection. It is a single layer of carbon atoms arranged into 2D hexagonal honeycomb structure. We're talking exactly one atom thick. Yet, this single, flexible atomic layer is actually among the strongest materials known to humanity. It's incredibly lightweight, highly flexible, which is perfect for bendable screens, and an absolutely excellent electrical conductor. We're talking super fast charging batteries and ultra-sensitive sensors. It is a true supersheet.
Next up, Section 4, Healing and Power Generation.
Now we're getting into biomaterials. These are specifically designed for medical applications, and they generally fall into three main types. First, metals. Think titanium, used for orthopedic joint implants because it's incredibly strong. Second, ceramics, which are absolutely perfect for dental implants because of their tough durability. And third, polymers, which are flexible enough to literally act as artificial skin. So what ties all these together? Biocompatibility, high strength, and corrosion resistance. Those three properties are exactly what make these materials perfectly safe to be integrated into the human body for a lifetime.
And on the power generation side of things, we have piezoelectricity. It sounds complicated, but it's basically the property of certain materials to generate an electric charge when they are physically compressed or placed under mechanical stress. Literally, if you squeeze this material, it magically creates electrical power. We actually use this principle everywhere. It's the spark generation in an everyday pocket lighter. It's in highly sensitive pressure sensors. And it's the core tech in advanced medical ultrasound imaging devices that let us peer inside the human body.
All right, let's wrap things up with Section 5, Exam Traps and Memory Tricks.
Okay, listen up, because here's your first major UPSC exam trap. The myth they will try to sell you is that graphene consists of multiple carbon layers. Do not fall for this. The fact is, graphene is strictly a single layer of carbon atoms. Just one. If it has multiple layers, well, then it's just graphite. You know, the literal lead in your pencil. Never ever confuse graphene's ultra-thin single-layer structure with a bulk material.
And here is the next trap, the myth that aerogels are dense materials. The fact is, they are highly porous and extremely lightweight. And honestly, this brilliantly illustrates exactly why we use the frozen smoke metaphor, right? If you just visualize a wisp of smoke floating in the air, you will never fall for the trap of thinking an aerogel is some heavy, dense solid.
So let's quickly lock all this in with some memory tricks. Whenever you see superconductors, I want you to think super equals zero, as in zero resistance. For nitinol, remember the secret is right there in the name. Nickel and titanium alloy. For aerogel, just think air-like gel, because it's almost entirely made of empty space. And finally, for graphene, think graph, like a perfectly flat, single sheet of carbon graphing paper. All right, let's do a super rapid-fire review to lock your knowledge in right before test day. Ready? Smart materials respond and adapt to their environment. Superconductors hit absolute zero electrical resistance. The Meissner effect causes that amazing magnetic levitation we see in maglev trains. Nitinol is your go-to shape memory alloy, made of nickel and titanium. Graphene is always just a single carbon layer, and piezoelectric materials generate electricity when you put them under physical pressure.
The progress we are seeing in material science is moving incredibly fast right now. Advanced materials, like nanocomposites, are getting lighter, stronger, and more conductive literally every single day. As these smart materials continue to evolve, they are completely blurring the line between biology and engineering. So, I'm going to leave you with this thought. Knowing that we already have materials that can heal themselves, levitate in midair, and remember their own shape, what impossible superpower will they unlock for us next? Keep studying, stay curious, and I'll catch you in the next explainer.